Hey, AP Physics students, it's Mr. Heinrich. We're looking at the next FRQ in Unit 5. This is FRQ 3 from the AP Classroom Progress Checks. Let's look at it. We have a group of students. They have this horizontal disc that can rotate on a fixed vertical axle at its center, as shown in Figure 1. A string of negligible mass is wrapped around a groove at the disc's edge, as indicated, and the diameter of the groove is measured to be d sub g equals 15 centimeters. The students notice that there is friction between the disc and the axle and wish to experimentally determine the magnitude of torque of friction exerted on the disc when it spins. The frictional torque can be assumed to be constant. The students are not able to remove the disc from the axle and the mounting platform or directly determine the mass or the rotational inertia of the disc, and that makes it tricky. They have access to a force probe, several rulers, a meter stick, and several stopwatches. All right, so that's the setup. Let's check out what part A is asking. Describe an experimental procedure to collect data that would allow the students to experimentally determine torque of friction by making a linear graph. In your description, include the measurements to be made along with the corresponding equipment needed for each measurement. Provide enough detail so that the experiment could be replicated, including any steps necessary to reduce experimental uncertainty. All right, so I think the easiest thing on this one, let's just develop the equation, and from that I will write the procedure because we're going to understand what we actually need to get the torque of friction from a slope of a graph. All right, there's our system. We've got this force that we're going to pull with, and we can measure this force from the force probe or the force sensor. We also have a meter stick, so I can measure this radius right here. And I'll do a little arrow there. I'll call that the radius R. It's hard to see on my drawing, but that's what that is. And you can see that this force times that radius would be my torque, the torque that actually makes this system spin. So I'm going to put F times R. And I know that I have both of those from measurements, but what did they say? They said there's this constant frictional torque. So even if we pull really fast or we pull slow, we're saying that that frictional torque is the same regardless. And if you watch the last video, you're going to remember there is a little tiny radius right here on the axle, right there, and there's a little tiny frictional force going that way such that we have a frictional torque. So this represents our net torque, right? And we know that net torque is equal to I of the disk times alpha. So that's a pretty good equation. And remember what we're actually looking for from the slope of our graph is the frictional torque. But the problem is we're going to speed the system up angularly, and then we're going to stop pulling and just let the thing come to rest on its own. So that's the idea. That means there's two portions to this problem. There is the angular acceleration and there is the angular deceleration. Actually, this side of the equation is way easier. Here we have two torques that are actually acting, but here, once we stop pulling with this force, the only torque acting would be the torque of friction. And we would call it a negative torque, and it would be equal to I of the disk times a new alpha. So I better call that alpha 2 and this one alpha 1, because these are two entirely different angular accelerations. The things I have in common between the two equations would be the torque of friction and the rotational inertia of the disk. So what I'm going to do next is develop something to plug in for alpha 1. And since I have a system of equations with the same two unknowns, I could easily get rid of ID and leave torque of friction there. But before we can do any of that, we need to address the alpha 1 and the alpha 2, because I have this force from the measurement of the force probe, and I have this radius from the meter stick, but how do I find alpha and how do I find alpha? What is alpha? Alpha is defined as the change in angular velocity with respect to time, right? And I'm going to say delta t1 because these two angular accelerations happen for different time periods, delta t1 and delta t2. So simultaneously, I'm going to take this and expand it. Now, it's really important to realize this right now. This final angular velocity that we accelerate this system to will be the same as this initial angular velocity when the disk begins to slow down over this time, delta t2. So I'm going to say that these two are equal. And what works well with these equations also is that my initial angular velocity is 0 when I begin accelerating the system angularly. And when the thing finally comes to rest, my final angular velocity would also be zero. So we have a simplification that happens, and I can further say that this would be equal to that, and this would be equal to that. And we'll take care of that negative a little bit later. It's going to go away. So now I have these nice expressions, and I can plug these in respectively to alpha 1 and alpha 2. And that's what I'm going to do next. And here we go. I'm going to plug this into that. So I have all the same stuff as right here times, I'm just going to call it omega because we know that this omega is equal to that omega. And we have negative torque of friction equals ID times, again, I'll just call this omega, not omega initial, but there's a negative right there, divided by delta T2. And you can see those negatives cancel out, like I said. So there's a lot of ways to go from here, but what I'm going to do is I'm going to multiply both sides by delta T1, and I am going to distribute it to both of these terms. And similarly, I'm going to take the delta T2 and multiply it to both sides. So here we go. I'm going to write FR times delta T1 minus torque of friction times delta T1 equals ID omega. And on the other equation, I will have torque of friction times delta T2 equals ID omega. You see it? This is pretty neat. We have these two left sides of the equations equal to the same thing. So that means this must equal this. So finally, I will write FR times delta T1 minus torque of friction delta T1 equals torque of friction times delta T2. Awesome. And I'm almost there. I will go ahead and I'll add this to the other side. I'll factor out the torque of friction. I will divide both sides, giving me FR delta T1 equals torque of friction divided by delta T2 plus delta T1. And check that thing out. That's awesome because I'm looking for the torque of friction from the slope, and you can clearly see we have a rise of this and a run of this. So I could actually answer part B right now, but let's go back to doing A. We need to write a procedure for how we got all of these quantities experimentally. All right, so part A, here's my procedure. 1, pull the string while timing with the stopwatch for some amount of time. Number 2, when you're ready to stop pulling, tell your partner to begin the other stopwatch. Synchronize this action and stop your stopwatch. Partner 2 stops their stopwatch when the disk comes to rest. And I totally forgot we need to talk about the radius. So I guess step 0, divide dg by 2 to obtain radius. Awesome. Okay, step 4, last step. Repeat steps 1 through 3 for multiple pulling times. And what I mean by this step is we're pulling for different amounts of time for each trial, maybe 3 seconds, 5 seconds, so on and so forth. But something else that we do need to say, and I didn't say, is that we need to pull the string with a constant force to the best of our ability. Okay, part A is done. Let's go on to part B, which should be very easy now that we have all of that development. All right, part B, for the data collected in the procedure from part A, describe how the students could create a linear graph and how that graph would be analyzed to determine the torque of friction. And basically, all this work we did is part B. So you want to show this work culminating with this equation so that you can finally say, given F from the force probe, delta T1 and delta T2 from stopwatches, I'll just write SW here, and radius graph, and I'm running out of room, but you would write graph FR delta T1 on the y-axis and delta T2 plus delta T1 on the x-axis. This rise over run would yield the torque of friction according to the equation shown. All right, cool. Let's move on to part C. Look at all those words, waiting for you to read them. Go ahead and pause it. You can do that if you want to. I'm not going to do it, but I am going to tell you what's going on here. We have an old school merry-go-round and we have this force sensor and we're going to pull it perpendicular to this radius. The radius is 2 meters and we're going to do this 5 different times at varying force amounts. And while I pull, you can see that we have a time associated with that pull. So this is the time of the pull. So for 40 seconds, I pulled at 7.5 newtons. At 20 seconds, I pulled at 18 newtons, and so on. But then what is this time T8? So this time is after we're done pulling. So when we're done pulling, there's no friction in the axle. It tells us that, or it's negligible friction, and the thing just continues to spin. And for 8 revolutions, we time it, and that's what this time is all about. So given that information, let's look at part C. All right, part C1. For a graph that has F average on the horizontal axis, indicate a measured or calculated quantity that can be plotted on the vertical axis to yield a graph whose slope can be used to calculate an experimental value for IDB, which is the rotational inertia of the disc bar system that you see here. So once again, they're helping us out. They're telling us on the horizontal axis, we have to put F average. But on the vertical axis, I'm just going to tell you the answer, and then I'm going to prove it to you. On the vertical axis, I would like you to write 1 over TF times T8. I'll say it again, 1 over TF times T8. That's what we're going to plot on the vertical axis. And I'll show all those values here in this margin when we get to part C2. All right, this part is a lot easier than the previous part. We have a force that's acting like that. We have a radius that's given to us at 2 meters, and we're calling that RF, and we're calling that RF. And this force is found from the force probe. So since there's no frictional torque in the axle, my torque net, which is equal to I alpha, torque net is simply that force times the perpendicular radius. And I is what we're looking for from the slope of the graph eventually in part D times alpha. Now remember what alpha is. It is the final angular velocity minus the initial angular velocity divided by the time. Now what time are we talking about? We're talking about the time that we actually applied that force. So this would be TF. And my initial angular velocity is 0. So from this expression, I need to ask myself, what do I not have? I got it, I got it, I got it. What's omega F? And this is where T8 comes into play. So I speed it up to this angular velocity, omega F, and then I just let the thing spin for 8 revolutions. And while it's spinning for 8 revolutions, it maintains that angular velocity for that time, T8. And this allows me to use the average angular velocity equation to find this omega final. I'll say and omega final would be equal in this case to the average angular velocity, which we know is just delta theta over delta t. And delta theta in radians would be 8 times 2 pi radians divided by the time of 8 revolutions. So the next version of this would be just 16 pi, and we'll leave off the radian. We don't need to consider the units right now, over T8. I'm going to take this expression and plug it in right there. So I'll get F times RF equals my rotational inertia of the disc bar system times 16 pi over TF T8. So you can see I just put TF in front of the T8, but right there is my omega F. So at this point, what I'm going to do is I'm going to take all of this terminology right here, and I'm going to divide it to the other side, and I'm going to flip the expression. So here we go. I get 1 over TF T8 equals F RF divided by I dB times 16 pi. And one more time, just to show you what I'm really getting at, I'm going to say 1 over TF times T8 equals RF over 16 pi. I'll move my constants to the front, I dB times F. What did I just do? I said that Y is equal to mx, right? I have to put F on the x-axis. They told me I had to do that. And my slope will not directly give me rotational inertia, but once I have the slope, I can set it equal to this expression right here. And I've got my y, which is what I told you at the beginning. On the vertical axis, we're going to put 1 over TF times T8. So now I'm going to input all those values into the table so that we have them for our graph. And to finish off C1, if the quantity you indicated is not already provided in the table, use the remaining column to record values of the quantity, including units. And that's what we have right here. Our unit is 1 over second squared. And these are all our values for 1 over TF times T8. So write them down. All right, C2, on this grid, plot the data points for F average and the quantity indicated in part C1. Scale, label, do all this stuff. Okay, let's do it. So our x-axis is force average, and we can see our scale is 2, 4, 6, 8, 10. So every one of these boxes is 2 newtons. And over here, there's our y-axis. We are measuring 1 over s squared, and every one of these boxes is worth 0.00004. And if you think about it, it makes sense because this would be 0.00008, 0.00012, 0.00016, and then finally 0.0002. Every 5 boxes, we go up by a value of 2 in our 10,000ths place. If you're wondering how I got that, this is how you scale the graph. You would take your highest value, which is 0.00097, and divide it by your number of boxes, which is 25. And what I got on my calculator was 0.00038. And I knew if I rounded that up to a 4, that I would have the counting system that I just went over with you. So I'm going to put all the data in right now so we can just save some time. All right, C2 is almost done. We have all of our data plotted, and it actually wasn't as bad as I thought it would be. If you see right here, we have 0.0004, and then 6, and then 0.000, almost 8. And so I was able to go right to those increments, and so they gave us nice data. They made it a little bit easier for us. On part C2 here, they also want us to draw our line of best fit. All right, let's draw our line of best fit. Averaging out the data, kind of looks like that is it right there. Boom. All right, I like that line. It's a good average. Let's find some perfect intersection points on the graph paper. And I see one right here. Circle that one. And I also see one right down here. So those are my 2 points. I made them hollow circles so you can easily see them. Let's write down the ordered pair that goes with each one of those points. Okay, there's my ordered pairs. I'm going on to part D. Using the line drawn in part C2, calculate an experimental value for IDB. So first and foremost, I'm going to find my slope, which is equal to y2 minus y1 over x2 minus x1. And I would have, remember this is 1 over second squared minus all over x2 newtons minus 2 newtons. And from this math, we get a really small answer. Yes, we should probably use scientific notation at this point, but whatever. So I'd have 1 over second squared over newtons, and I could multiply top and bottom by 1 over newtons. I would get this. 1 over second squared times newtons. That is my unit for this weird slope that we have. But remember, from our equation that we developed way back when in part C1, we got that. So this number right here is equal to all that stuff right there. I would have IDB equals RF all over 16 pi times my slope. You follow? All right, so let's finally find IDB. IDB is equal to RF was given as 2 meters divided by 16 pi times a really small number. And by dividing by this really tiny number, I am going to end up getting a reasonable answer. For IDB, I would get 255 kilogram meters squared. And that is my answer. Now, if you're wondering how those units worked out, check it out. I'll do a quick unit analysis. Meters, multiply top and bottom by second squared newtons, and you would get meters times second squared newtons. A newton is a kilogram meter per second squared. Second squared cross out, and you have kilograms times meters squared, what I originally said. Okay, so we made it through a long FRQ. Thanks for sticking with me. Like, subscribe. The next one is coming soon. Mr. Heinrich, I'm out of here. Talk to you later.